Okay, everyone, welcome to tutorial 2. This is our model that we built in tutorial 1, and hopefully you've had a chance to work through exercises 3 and 4 on your own before either looking at the PowerPoint slides or before watching this video. So if you're watching this video now and haven't tried exercises 3 and 4, please stop it and try the exercises. I think it'll be really helpful if you can try it. Okay, so let's get going. So basically, once we built this model, what we had was a population that went crazy, right? So after 60 years, the Roadrunners are overrunning the island. There's 1,000 Roadrunners on the island at that year 60. So basically, the residents start to say, okay, we're going to allow hunters, like this hunter here, to kill the Roadrunners in order to get the population in control. And they're going to institute a hunting quota, which is a fraction of the Roadrunner population that can be hunted each year. So 5%, 10%, 15, 20, 30%, whatever is the population of Roadrunners that hunters can kill each year. So we're going to use Vensim to answer these two questions. First, what must the hunting quota be in order to achieve this stable population? And then what must this quota be to eliminate all Roadrunners within 20 years. So let's work through Vensim to see how we can answer those questions. So here's our model, right? Notice how we can, one thing I didn't show you before is with these sliders, we can move our model up and down. So that might be kind of handy for later. But basically, the question is, how do we add hunters to this model? Well, essentially what we'll want to do is click on the variable tool. And the reason we chose a variable tool is the hunting quota is going to operate very similarly to a death rate, right? It'll be the rate of Roadrunners that are killed by hunters each year. So it's going to be just like a death rate. It's just going to be called a hunting rate or a hunting quota. So we'll build that right here. This is hunting quota. I'm sorry if my keys are a little loud. I apologize. I'm trying to do it as quietly as possible. So that's our hunting quota. We can hit enter on that. Now let's go to this arrow tool and connect hunting quota. But what are we going to connect it to? Again, it's going to operate on deaths more than it operates on population. It'll obviously operate on population, but through deaths, right? So hunting quota is going to affect deaths. The number of Roadrunner deaths we have is a function of the hunting quota. So we're going to connect these two. So let's click that arrow, click in hunting quota. And I want to sort of show you real quick what happens if we don't click in Roadrunner deaths. Let's click over here. See how when nothing happens, it just becomes a line that then we can turn into another line? This wants to connect to something. Hunting quota wants to connect to something. So Vensim doesn't like when it doesn't. So let's click in Roadrunner deaths and boom, we get our nice little blue arrow. If we wanted, we could go like that, but I'm just going to keep it a straight line for right now. Okay, so now we can click on our equation tool because we've got our model, and essentially what the model is telling us is, oh hey, you need to define a hunting quota. So in the slides here, I tell you to try 0.1. And then that's not going to be perfect, so we'll use SynthSim to see what makes the population stable. And the reason we guess on this is this happens in modeling a lot. Sometimes we'll just guess on an equation to be a placeholder so we can build out the rest of the model. So I'll do that all the time when I build a systems dynamic model for the banking industry or something. I'll just throw sort of placeholder equations in just to get the structure of the model working. And then I'll do some research in the literature and go back and fill in those equations. So guessing equations is actually quite common just to get a placeholder. Or you might know it from the get-go. So we're going to go at 0.1 here. That's the hunting quota. So 1 out of every 10 Roadrunners will be killed each year by hunters. And then we'll click on Roadrunner deaths here. And we see that Roadrunner population times the Roadrunner death rate is that initial, the initial number of deaths. But now we have to add in these hunting quotas. So we've got our Roadrunner population times the Roadrunner death rate, And that is, actually, you know what? I'm going to interrupt myself real quick. I'm going to run this equation without adding in our hunting quotas, just so you can see an error. I'm going to click OK, close this. Well, maybe see how it says it won't allow expected a name or a valid expression. So it's expecting hunting quota and we're not giving it. So that's going to be a problem. It'll never let you run that model. So let's add that in. And the Roadrunner deaths that are contributed by hunters are the hunting quota times this Roadrunner population. Let's check that syntax. The equation is okay, and let's say okay. So that works now. One thing we need to remember to do, though, is change this Roadrunner population. It was in 50, and we need to change it to 1,000 because that's the new beginning of the population. So your model would have started with 50, and we just need to start it at 1,000. Okay. Now, let's see what happens. Let's insert an IO tool so we can see a graph here as we run a synth sim on this. Let's do a workbench tool. We'll call it a graph, and we're going to have a variable name in here called Roadrunner population. Again, we just can close out of it, and here's what's going on. I'm going to move this down a little. Here's what's going on with this Roadrunner population. See how it's dropping pretty precipitously. So I'm going to run a synth sim in here. Click yes. And this is what's going on with our Roadrunner population when a hunting quota is 0.1. Dropping really fast, which means what? When the population is dropping really fast, it means the hunting quota is too high. So let's change this. Actually, let's just see what happens when we go even higher. See how that population drops even more precipitously? It's kind of cool. It drops really fast when you're able to kill 0.6 out of every one coyote. Roadrunner, essentially you can kill 6 out of every 10 every year. That's going to make that population crash, and we see that. So let's go lower. That's actually somewhat more stable than when we started at 0.01. So at 0.056, it's a little more stable, but still dropping. Let's go a little lower to, well, when we go to negative, obviously a negative hunting quota is not going to be good, but 0.125, that's still dropping. Let's go 0.056. Let's get a little smaller than that. 0.022 is somewhat stable, but still going up. So we know that this needs to be somewhere between 0.02 and 0.056. So let's try this out with hunting quota. Let's just do 0.05 and just see what happens. Let's run a synth sim on this. And we'll see this graph straightens out at 1,000. So let's close that. We can also just run this model if we want. And once we've run that model, we can run a graph. Well, not on hunting quota. We'll run a graph on Roadrunner population. And we can see that Roadrunner population is flat at 1,000. Now, Vensim isn't always perfect at working these graphs. And the reason is these graphs aren't meant to be perfect output graphs. They're just what you want to be working with as you build your model. So if we want to see something, what we could do is build a custom graph for Roadrunner population. Roadrunner population. In this custom graph, we're going to select Roadrunner population here, dataset current. And we're going to set our Y min to be 0, which is fine, but we're going to set our Y max to be 2,000 because for some reason the current situation isn't going to work too well. And we're just going to display that. Boom. And now you can see with this new custom graph that I built, it's the same as here. It's stabilized, but the y-axis is different. So we can see that at a hunting quota of 0.05, this population stabilizes at 1,000. And that makes a lot of sense intuitively as well. This Roadrunner birth rate is 0.2. The death rate is 0.15. So when the hunting quota is 0.05, that means births of 0.2 equal total deaths of 0.2, and we get a nice situation where it's in equilibrium. Okay, but then the question says, What must the quota be to eliminate all roadrunners in 20 years? Well, let's see what we can do here if we run a synth sim by changing this quota. So if we want to go decrease to 0 within 20 years, we need to increase that hunting quota. So let's see what happens as we increase that. So we increase it to 0.19. That decreases it pretty fast, but not in 20 years. If we go to 0.46, that decreases it, looks like just a little shy of 20 years. So maybe something a little lower, 0.39. That looks like it might be close to 20 years. So what we're going to do is I'm going to close out of this. I'm actually going to change this hunting quota to 0.4. And we're going to run that. Okay. Now I'm going to go into my custom graph and display this population, and we can see that it crashes here. But what I'm going to do is edit this, because instead of 2,000 on my Y max, I'm going to make this 5. So I'm going to really zoom in on this graph. So we'll click on it again and display it. And what we see here is these are the same. It's just really zoomed in over here. And what we see is how we hit 1 in year 20. We hit 2 roadrunners in year maybe 17 or 18. We get less than 1 after that, but a roadrunner can't mate with itself. So we're at 1 at 20. So at a hunting quota of 0.4, we get less than 2 at year 20. So at year 19, these 2 roadrunners could mate and could create more roadrunners. They can't any longer at this rate, and that's why you see it drop so quickly afterward. This one is 1 left and is going to be by itself, but it'll die then in 10 years. So that 0.4 is going to stop that roadrunner population, and we can see that on the answers here, that a quota of 0.4 or higher reduces that population to less than 2 in 20 years, but that stable population happens at 0.05. Okay, great. Now that we've answered exercise 3, let's hop into exercise 4. Exercise 4 is a little more complicated, but not too bad, actually. Basically, what we've got is these villagers on this island say, we don't want all these hunters. Maybe bullets are flying and it's dangerous or what have you. So they outlaw hunting and decide to instead bring a population of 60 coyotes onto the island to naturally take care of this roadrunner population. Now, since we've got 2 populations, we kind of change the population models for each, for the roadrunners, and then by default as well, the coyotes. And the reason this happens is roadrunners are now dying not just of natural deaths, but they're dying as a function of coyotes finding them and killing them. Okay, so this roadrunner births is a function of the roadrunner birth rate, this alpha here, times the roadrunner population. The deaths now are this beta, which is this death rate times the roadrunner population, which is pretty normal, but now it's also multiplied by the coyote population. And the fact that we do this beta times the roadrunner population times the coyote population, this is what's called a proportionality constant. And the proportionality constant essentially says that roadrunners die at a rate that is proportional to the size of the coyote population. Now, that might be an assumption that you're not comfortable with and you'd like to build a different model. That's totally fine. You can build different equations for that and they could be correct. A lot of biological modeling uses this proportionality constant, and it works really well because it does end up being true that populations of prey are dying at a rate that is proportional to the population of their predators. So this proportionality constant works really well, and this ends up being this equation right here. Right? This beta times roadrunners times the coyotes. Now, we also see this proportionality constant operating here on coyote births because coyotes are eating roadrunners. The more roadrunners there are to eat, the healthier and more fecund the coyotes become. So we see this proportionality constant that the coyote births become this mu birth rate times the roadrunner population times the coyote population, right? So it's similar to the death rate, but it's of roadrunners, but mirrored in the birth rate of coyotes. So these are how the two populations are going to interact. So let's build this model. So let's start here real quick by deleting this IO. Let's get started. How do we do this? Well, first we need to get rid of that hunting quota because hunting has been outlawed. So that's easy enough. We just have the trash can tool and click on it and our hunting quota is gone. Let's also make room for coyotes. So we're going to move by dragging along here, by dragging the sliders, we're going to move that roadrunner population model a little lower. And now we're just going to build our coyote population model. The coyote population model is really going to be quite similar to the roadrunner population model. Most population models are really similar. This is a very basic one, but it's going to operate for humans this way, for algae, for pretty much everything. So we'll build a similar coyote population model. Coyote population, enter. And that stock of coyotes will be a function of a flow of coyote births, and we'll going into that stock, and then coyote deaths leaving that stock. Now, one thing I haven't shown you a lot is we can move this. So I could move this flow down to here, up to here. I can move this stock up to there. Right? So you can move things around as you need to. See that? I'm not going to do that. But that move tool allows you to move a lot of things. All right, so what else is needed? We need a coyote birth rate. And we need a coyote death rate. We need to connect these again like we did before, and we're going to connect them similarly. The coyote population informs the coyote birth that we have. I'm doing this opposite this just to clean it up. You could easily do it this way too if you wanted, but I'm going to do it here. The coyote population also informs the amount of deaths that we have of coyotes, right? So we've got this beginning to look like a model. That birth rate, just like with the roadrunners, informs the births. So now we see that births are a function of the coyote population and the coyote birth rate. And then this coyote death rate feeds into coyote deaths in much a similar manner. I'm going to move that over so that it fits here. There you go. So it looks a little cleaner. Boom. So now we've got this kind of nice model. How do we connect these two populations? We need to, and we know that when we look at this equation, they're related through the roadrunner deaths and the coyote births. So let's go into that. The roadrunner population creates coyote births because the more coyotes there are, the more roadrunners there are, the more coyotes will be able to eat those roadrunners, and that will lead to higher levels of coyote births because they're so happy and full and healthy and able to mate with one another to have to increase births. And then the more coyote population you have, the more roadrunner deaths you have. So as the population increases for coyotes, you're going to increase the number of roadrunner deaths. So see how they're sort of symmetrically related in this situation where the population of coyotes drives roadrunner deaths and the roadrunner population drives coyote birth. So they're related in this model. And this is why it's a predator-prey model. Coyotes are the predators of the roadrunner prey, and that's why you see the coyote population feeding into roadrunner deaths and roadrunner population feeding into coyote births. If they were both predators and prey of one another, you might have arrows that go the other way as well. Or if the roadrunners were the predators and the coyotes were the prey, it would be opposite, where this population would go to that death and vice versa. But this is the situation now, and this is our nice little model. Well, so now we can define all of our equations. So let's click on our equation tool, and it's going to tell us what we need to define, and that's a lot. So let's start with the coyote population. We know that it's births minus deaths because Vensim tells us that, and that's correct. The initial value is 60. Okay, so we can keep it. We're good right there. That was an easy one. We know the coyote birth rate is 0.00015, and we know this because I gave it to you in the equation. That's the proportionality constant of the coyote birth rate is 0.00015. That is mu. The death rate of coyotes is 0.15, and we know that, again, because I gave it to you. Coyote deaths, again, Vensim's going to nail this one for you. It knows that it's got to be these two, and we know that deaths are population times the rate of death. And click OK. Now this is where it starts to get tricky. Let's look at roadrunner deaths. See how we've got that hunting population in there? Let me click OK and see what happens. Hunting quota is not a variable name, right? So it sees hunting quota in here, but there's no arrow that's called hunting quota connecting anything. So we know we need to remove that before we can do anything. Let's remove these parentheses as well. And now we know that roadrunner deaths are the roadrunner population times the roadrunner death rate times that coyote population. And again, that's because of this proportionality constant that we worked through there. So we can click OK. So that's the roadrunner death. Then coyote birth is going to be similar. This is going to be our coyote population times our coyote birth rate times the roadrunner population. Again, these are related through that proportionality constant. And we're good. Now I'm going to actually run this model for you because we have forgotten to do one thing, and I'm not going to tell you yet. I just want to show you what happens when we run this model. So click Run the Simulation. We're going to click Yes to this and see what happens. It says unable to achieve desired accuracy and integration time. Basically, the model got so big it exploded before a single year. And the reason that's the case is, don't forget, this roadrunner death rate used to be 0.15. And once we've introduced coyotes, it actually changes to 0.002. That's the new roadrunner death rate. And we didn't change that. And the reason we didn't change that is Vensim didn't know it needed to be changed. Vensim only tells you to populate equations that it either sees problems with because of arrows, or there's no equation in and it requires an equation. Roadrunner death rate has an equation of 0.15 at that constant. It didn't know that we changed our model. So it's at 0.002. Now that we fix it, now this should work just fine. So let us run a single simulation. And it works just fine. There's our model. Now, I'm going to have us figure out what's going on with this thing. So we're going to do a custom graph called new, let's call it population dynamics. And we're going to select a variable coyote population and run it off of dataset current. And then we're going to select roadrunner population and also run it off of current. This is so cool, these custom graphs, because we could actually, if we were running multiple different runs and naming them test 1 or current 3, whatever we're doing, we could run different variables against different data sets and see how different things are interacting. But we're not for this. And I want to run an X division of 10. And all this is basically doing is allowing us to have nice clean lines on that x-axis. It's not necessary that we do this, but it's much easier for us to see these divisions along the x-axis on this graph. Okay, so let's click OK. And let's take population dynamics display. And now we've got a nice little graph that says what's happening with our pretty sweet model. Now let me explain what's going on here. This is pretty cool. We see these two populations oscillating back and forth. This makes a ton of sense. As the roadrunner population increases, the coyote population increases because they're eating them. But what happens is once you get here, maybe to about 10 years, there's so many coyotes that they're eating all the roadrunners. So the roadrunner population starts to crash. But since roadrunner deaths are a function of the coyote population, and the coyote population is a function of coyote births, which is a function of roadrunner population, all these dynamics have to happen year over year over year. So there's going to be lags because of how these populations are filled and are created. There's going to be year and multi-year lags. So we see that this roadrunner population starts to dip around 10, but coyote still keeps increasing because there are plenty of roadrunners to eat. Until you get to this point right here around maybe year 17, where this roadrunner population has dipped so low that the coyote population can't grow anymore, and it then starts to crash. But again, as this starts to crash, roadrunner will continue to crash, coyote will crash until the point that there are a few enough coyotes that the roadrunner population won't be eaten as much and will start to recover and shoot up. And again, the dynamic plays over. And you see that there's this oscillation where the peaks are about 5 years off from one another. You can see that the axis here is 2,000 for roadrunners and 200 for coyotes. So we see this dynamic on different axes, which makes it really nice so that we can play them in real time. If I go to custom graphs here and edit population dynamics and click scale here, that'll put these to scale. And let me show you what happens. Population dynamics, display, all of a sudden you get the graph that looks like this. So it's the same graph, it's just done in the same scale. And this is really handy. Sometimes you need that. But you can see this coyote population much lower and oscillating differently. So I'll go to population dynamics and edit that. Turn that scale off. And the scale, you can click between these variables because sometimes you won't want, see how you can have up to 6 different variables. Sometimes you might want them scaled, sometimes you might not. So there's a lot you can do with these graphs. But again, I'm going to go to display this population dynamic. And this is basically what's going on. I think this is a pretty cool simulation. Let me run a synth sim real quick and show you something that I think is funny. I'll just run an override yes. Let me do the roadrunner death rate and shoot it through the roof. See how it pops and turns red there? Basically, the model explodes. So you can sort of see what's going on. But also it's interesting just to look at all the stocks and flows and what's going on as just the roadrunner death rate changes. You can see how intricately linked everything is. It's pretty gnarly. I just said gnarly, I'm really sorry. I'm an 80s baby. Okay, so that was tutorial 2. Hopefully that made a lot of sense and you got those questions correct when you tried it yourself. Your model doesn't have to look exactly like this. Your equations in the structure have to be like that in order for it to work correctly, but it could look any number of ways. You could have put coyotes on the bottom, birth rate could be over here, right? As long as the bones of the whole system are the same, you're going to be fine. And this is actually how we're going to assess you if you choose to do the assessment for systems dynamics modeling. We're going to get some sort of a complicated model like this. And there will be policy interventions such as hunters or other things that you can manage stocks and manage flows given policy interventions. And that's just a really quick way to say that the assessment will be something like this. Much more difficult, but something along these lines. All right, so hopefully System Dynamics has been fun for you. Vensim, I think, is super cool, and as you can imagine, it can get really complicated, and I've just gone through some quite basic stuff with you. But this should have helped with exercises 3 and 4, and I appreciate you hanging out with me for these last couple tutorials, and hope you enjoy yourself. Thanks a lot.